Okay, in this video we're going to take a look at graphing polynomial functions, which we did a little bit last time when we were looking at the different shapes, but we'll get a lot more into it here. So maybe let's just start with an example of a function. Say f of x is equal to x minus 1 times x plus 2 all squared. So there's some function. Notice it's already been factored for us, and we want to sketch this. So here are the steps to doing this. First of all, we want to find all the x-intercepts. And we do that by solving f of x is equal to 0 and factoring. Now, in our case, this is already factored. So we've basically got a factored form. There's your first factor. Here's your other two factors. So now we can find the x-intercept, just simply make f of x equal to 0, and when do we have these parts equal to 0? Well, if this is equal to 0, which is when x is 1, we have an x-intercept, and when x is equal to -2 or -2, because there are two factors, I'll write this one out twice, and that multiplicity will become important when we draw our picture. Second step, find the y-intercept. And we do that by making the function, finding the value of the function when x is equal to 0. So our function when x is equal to 0 is 0 minus 1 times 0 plus 2 squared. And so that's minus 1 times 4, which is -4. And so I now have a y-intercept. So I have my x-intercepts and I have my y-intercepts. Next, we are going to take a look at using multiplicity to determine the shape at each x-intercept, and this is a bit new. But this is how it works. If you have a x-intercept that happens once or 3 times or 5 times, so if your multiplicity is odd, type of x-intercept you have, so here's an x-axis here, here's your x-intercept. The type of x-intercept you have is the fact that the graph goes through that point smoothly, like from the negatives to the positives. It could actually go this direction as well, but what I'm saying is it goes from above the x-axis to below the x-axis, or from below the x-axis to above the x-axis. So it goes through that point, as in right across that x-axis. Something quite different happens if the multiplicity is an even number. So up here we've got one that's even and we have one that's odd, so we'll see both of these in this example. But if the multiplicity is even, so that means your x-intercept has happened more than one time. When you solve, you get the same answer more than once. Then what happens as you get close to that x-intercept, so this is our x-axis, here's the intercept, the graph comes towards it, it touches that point, and then it goes away. So it looks something like this. If it's coming in this quadrant, it comes down, it touches, and it goes away in this direction. So it'll do either a bounce or a bounce, and it'll stay. It won't go through to the other side of the axes. So, and that's true if it's a multiplicity is odd or multiplicity is even. Each of those is true. So I know that on my graph for this one, x is equal to 1 right here, it goes through this point. Or, and I'll just draw this in a different color, maybe it goes through this point this direction. And at -2, I know that it bounces. So maybe it bounces like this, and maybe it bounces like this. I'm not 100% sure how that works yet. We need some more steps to this. I do know though that the y-intercept is -4, so if this bounces up, it's going to be hard to get to a y-intercept of -4. So, because it would have to come back down, which means there would be another x-intercept, and there isn't. So that gives me a bit of a clue that it is actually this red graph, and I guess it goes down here and then it comes back up like this. So I get some more information when I start to put these things together, that it might look a lot more like this red graph. Let's keep moving on and see what the next few steps help us determine. Well, last day we took a look at how the leading coefficient and the degree helped us determine the overall shape. So I've got the function f of x is equal to x minus 1 and x plus 2 all squared. And if I do a little bit of work here to expand this becomes x squared plus 4x plus 4, and I expand using distributive laws, I get x cubed. And really I don't need to do anything more than once I've got this x cubed term, because there's my highest degree term. That tells me what the shape is, and the leading coefficient to this is a positive 1. That tells me more about the shape. So from last day, a cubic looks like this when it has a positive leading coefficient, and that gives me more ammunition to determine that this graph probably looks a whole lot like this, so that those two blue shapes match up. Let's continue to see if this is correct with step 5. And in step 5 we are going to determine the number of turning points. And what I really mean by this is determine the maximum number of turning points. And from last day, the maximum number of turning points is the degree, which is 3, minus 1. So the maximum turning points is 2. And if I take a look at my graph, I've got 2 turning points. I have what I called a hill last day and a valley, and I have 2 of them. Next, we can actually estimate what the highs and the lows are. So if I reproduce the graph here, I knew that it had a bounce here at -2, it went through -4, and it went back up here through +1, and up like this. But I can actually estimate how far up and down these things are. Like, is the -4 at the bottom of this curve or not? And one trick to doing that is simply saying, okay, how far is it between these 2 points? And if you found the estimate, which is, or the middle of this, which is maybe about -0.5, then you can try and see if that is, does this go down like this and then come back up? Or does it maybe go down here and then back up this way? And to do that, just simply calculate what the value is of the function at f of -0.5. So we've got our equation here, and that's squared. Simply put -0.5 in and -0.5 in here and see what value you get, which is about -3.4. So it's still, at this point, it's still only -3.4, so it's still falling and then coming back up. And that gives you a bit of an idea of the shape. I mean, one really slow way to do any kind of graph is just create a table of values, right? Create a value table, and so that's what this is. If x is -0.5, what's f of -0.5? And that's -3.4. I mean, it's really slow to plot all those dots, so I'm trying to find faster ways to do that. And these 6 steps plus one more, which I've actually already done, are a very fast way of doing this. And that last step is, once you have all this information, all polynomial functions, as I mentioned last day, are smooth continuous lines or smooth continuous curves. So the last step is just to draw the best fitting smooth continuous curve. And so I don't want to see a graph that goes like this with a bunch of straight lines. We definitely want to make sure that you have a nice smooth curve to your graphs. Okay, here's the second example, and I'll do all 7 steps, and I'll do it fairly quickly here, but we're going to sketch, and I'll give a much more complicated graph here. F of x is equal to x plus 3 squared, x minus 5 squared, x plus 1 cubed. And you notice I'm giving these to you in factored form. Later in the unit they won't be in factored form, and I'll have to teach you how to get it there, which is a little bit tricky. But let's start by putting a bit of a sketch down. So what do we know about this? Well, we know some x-intercepts. We've got -3 and -3, and we've got 5 and 5, and we've got -1, -1, -1. So this is some kind of a bounce. This is another kind of a bounce, and this one goes through, either straight through this way or straight through that way. I can calculate my y-intercept, just make x equal to 0, so I get 0 plus 3 is 3 squared, that's 9, minus 5 squared is 25, and 1 cubed is 1, and so my y-intercept is really big, 225. Then I want to look at the leading coefficient and the degree. So if I distribute this, expand all of these terms out and multiply, this term here ends up being x squared with a leading coefficient of 1. This term here turns out to be an x squared with a leading coefficient of 1. And this will actually be an x cubed. And I don't need to expand all the other stuff. So I now know that this, when these were multiplied together, this will be a degree 7 equation, 2 plus 2 plus 3. And I know the leading coefficient, 1 times 1 times 1, will be positive. And from this I also know the maximum number of turning points. So now I can start to sketch this. I know at negative 3 it's going to bounce somehow. Oh, one other thing is I know a degree 7 positive equation. So degree 7 is odd, so it'll come up, down, up, down, up, down, up. It'll look something like this. So I know that it comes from the negative kind of infinity quadrant 3 area, and it comes up. And at negative 3 it bounces. So it comes up and it bounces back down. I know that it goes through a y-intercept that's way up here. That's 225. So my scale is a little crazy here. I know that it also has a triple multiplicity of 3 at negative 1, which means when it comes back up, it goes right through that point. It must skyrocket up here, and then it's got to come back down to 5. 1, 2, 3, 4, 5. It's got to come back down, and it does a bounce at 5. So I don't know where it goes up to, but it comes back down, and at 5 it does a bounce, and it goes back up. So my graph could look something like this. I certainly know that it goes down to negative infinity in quadrant 3 and up to positive infinity in quadrant number 1 from the overall shape of this graph, and the maximum number of turning points is 6. So I see a hill, then a valley, then a hill, then a valley. That's only 4, but that's okay. It says maximum of 6, so that fits quite nicely. And I've got my x-intercepts. I've actually already drawn a fairly smooth curve. I can indicate that's negative 3, that's negative 1. I've indicated the other x-intercept is 5, and what the y-intercept is. The only other thing that I could go and check is, okay, between these two, negative 3 and negative 1, at negative 2, at the average, what's this graph worth? So I can plug negative 2 into the original equation and see if this is essentially creating another data point on my graph, see if I'm down into the negatives. So negative 2 plus 3 is 1. And so this is f of negative 2 that I'm calculating. Negative 2 minus 5 is negative 7 squared. And negative 2 plus 1 is negative 1 cubed. And so I get 49 times 1 is 49 times so I get negative 49. So this is down to negative 49 in this direction. My scale is quite different in my y direction compared to my x direction. Then I could check between 1 and 5, and the average of 5 and negative 1, add them together is negative 4, is 2, divided by 2. So I could check, maybe there's a high value around negative 2, and I could check f of 2. I should get a very high value for this, so I get 2 plus 3 is 5 squared, and then I get negative 3 squared, and then I get 3 cubed, and this is a very high number. In fact, I get about 6,075, so this is increasing way higher than my graph is showing if this point here is somewhere in the 6,000s. But it gives you an idea of what this graph looks like, and again, we are only sketching, so I'm not even using graph paper to do these because I just want to get an idea of what these things look like. Okay, what happens if we have the roots and some information about the equation, but we don't actually have the equation? Can we go and kind of backwards engineer what the function has to look like? And that's what our next question is.